Dear student, today in this video we are going to discuss about energy stored in a capacitor. As we know, capacitor is a device which is used to store charge and energy. So today in this topic we will derive the formula for energy stored in a capacitor. So to derive this formula, let us consider we have two plates of the capacitor. First one is plate 1 and the second one is the plate 2. Both plates are initially uncharged. There is no charge on these two plates. So now we will give some charge to these two plates. So how we will give? Because both plates are initially uncharged. It means these plates are neutral. When a body is neutral, it has equal amount of positive and negative charge. If we consider second number of plate, this is a neutral plate, and in a neutral plate positive and negative charge equal. So it means in this plate positive and negative charges are equal, and similarly in the plate number 1. So positive and negative charges are equal. Now we want to give charge to these two plates. So we will do something so that this plate become negatively charged and this one become positively charged. So we will do by using some external agency, we will transfer the positive charge of this plate, the plate number 2, because this plate has these electrons and positive charge. You can say equal number of positive and negative charge. If we transfer this positive charge from plate 2 to plate 1, then what will happen? Yes, we are going to shift the charge from this plate to this plate. For example, if you have 100 electrons and you want to hand 100 electron negatively charged particle and proton, and you want to transfer 100 positively charged particle from this body to this body. So you have to transfer these two charge in installments. Like you can transfer first 2 positive charge, then second time 2 positive charge. In that way you can transfer the positive charge from this body to this body in small installment. Okay, so we can see here we are transferring the charge, positive charge, from body 2 to body 1 in small installment, and each installment dq charge we are transferring from plate 2 to 1. So what kind of final stage we will get? This whole positive charge start accumulating here. Let us consider we have shifted the 50% positive charge from this plate to this plate. But what about the 50%? When you are transferring the charge from here to here, positive charge, because here already positive charge is there and you are bringing positive charge from here to here, so there is a kind of force will develop that is known as repulsive force. This plus charge is not allowing to accumulate the another plus charges. So because of that these charges feel repulsion, but we want to transfer the charge from plate 2 to plate 1. It means we need to do some work. So that work is stored as in the form of potential energy in the capacitor. As you can see in the next page, in that way you transfer the whole positive charge from plate 2. This is your plate 2. You transfer whole positive charge to whole positive charge from plate 2 to plate 1. So in this way here the positive charge developed and here only negatively charge is left. So while we are placing the charge from 2 to 1, second plate to first plate, that time we need to do work. So that work done we have to find, because we transfer the charge in installments, that small installment, that is dq installment. So initially when time is 0, when initially t is equal to 0 means initial condition, so q is equal to 0, there is no charge on the plate 1. There is no charge on the plate 1 initially because it was uncharged, and the second plate was also uncharged. So initially these two conditions are satisfying. Now we started the transfer the charge from second plate to the first plate. So suppose that time is t. So when time t is equal to t, so suppose we transfer q charge. That time we install, out of total q charge we transfer q charge at time t. When time is t and you transferred q much amount of charge from second plate to the first plate. Now but we want to transfer whole positive q charge from second to first one. So let us consider when time is infinity. So that time you have installed full charge from second plate to the first plate. So that time you can write q by q. So now what is the C at that time? When time is 0, capacity is not getting changed because capacity depends on the distance between the two plates and the area of the plate, and also on the medium of the capacitor. So capacitor will remain same even in this case also. C is same, capacitor is same, and here also C is same. So now what will in the first case the capacitor C will remain the same because time is 0, q is 0. What will be the capacitance in this case? So in this case you can write capacitance is equal to C is equal to q by v. V will remain same in all the cases. So C is equal to q by v. When you transfer the charge q from plate 2 to plate 1, this one is the capacitance. So now we have to find the work done. The small of work done need to transfer the charge from plate 2 to plate 1. So let us consider that small amount of charge work done is dW to transfer the smaller amount of charge, and we know this formula, potential is equal to V is equal to W by Q. So you can write here W is equal to V into Q, and we transferred the small amount of charge, that's why I wrote here dQ, because we transfer very small amount of charge one by one. So what is V? V you can write from this formula, that is Q by C dQ. So this is the small amount of work done to carry the charge from one plate to the another plate when time is t. Now we have to calculate the total work done to shift the whole positive charge from plate 2 to plate 1. So during this time we need to do the work, and that work is stored as a potential energy. So we will do the integration now. Integration of dW, which is equal to Q by C dQ. So now integration of dW is W, and now what are the limits? Initially what is the charge? It was 0. When time is 0, charge is 0. And now what is the final condition? When time is infinity, the capacitor is fully positively Q charge. So we will take here Q is equal to capital Q. So our limit will be 0 to Q. So now in the next step we will do the integration. So C is the constant, so we will take it outside, and here integration of Q, as we know Q dQ, we will do the integration of Q, that is we will add 1, so that is Q square by 2. So integration of this term Q square by 2, so limits 0 to Q, so it is 1 by 2C. And now we will substitute the upper limit and lower limit. So you will replace Q with the upper limit, that is Q square, and subtract the lower limit. So finally you will get this 1 by 2C Q square. So this is the work done that is stored in the form of the potential energy. Now next we will write different expression for this formula. So the first formula, as we know, we discussed here W, that is stored as a potential energy. So U is equal to W, that is equal to half Q square by C, and we know Q is equal to CV. From the definition of the capacitance we know this formula, so substitute the value of Q. So what you will get, half C square, B square and C. So you will get half CV square. This is the second expression. This was the first expression. This one is the second expression. And even we know CV is equal to Q. Again from this formula. So we can rewrite equation 2 as, you can write CV square. V square you can write V into V. So you know CV is equal to Q. You can put CV is equal to Q. So finally you got half QV. So this is your potential energy. So now we derived 3 formulas for potential energy, first, second and third. All these formula will help you to solve the numerical problem. So dear student, that is enough for today. Dear student, if you like my video and if you want more updates regarding my next video, so please subscribe and share my channel. Thank you.